Welcome back to GeoCrimeHub. This is part 2 of our two-part series on using multi-ring geographic buffers to analyze crime densities around a sample of Philadelphia public high schools. In part 1, we created two buffer types, non-overlapping rings and overlapping disks, and we touched on their advantages and trade-offs. Now we'll bring in the crime data, join it to those buffers, and calculate densities for offenses like theft, robbery, drug violations, and assaults. We'll see how the results differ across buffer types and what those differences can tell us about whether schools attract or protect against crime. And as a quick bonus, I'll show you how to calculate a location quotient that compares the outer rings to the 400-foot zones, giving us a simple ratio to interpret how crime changes with distance. To get restarted, I've opened up the buffer project we created in part 1, and you'll see that it still has both multiple ring buffer layers that we originally started with. So that's the overlapping disks and the non-overlapping rings. In addition, I've brought in Philadelphia Part 1 and Part 2 crimes for the past year, which I'll activate now. And you can see there are a lot of crimes. This is 1 year's worth of Part 1 and Part 2 crimes. If we open up the attribute table, we can get a sense of what we're working with here. As you'll see, there were 153,269 Part 1 and Part 2 offenses that occurred over the past year. And you'll see here that there's a text-generated code that tells us what these crimes are. If we right-click it and come under Visualize Statistics, it'll create a bar chart for us that gives us a visual representation of the distribution. You'll see that the top 5 crimes here are thefts, other assaults, motor vehicle theft, vandalism, and criminal mischief. Some simple math tells us that that's 107,152 crimes that account for the top 5 crime categories, and they account for about 70% of all crimes. When we talk about Part 1 crimes in Pennsylvania, where I'm doing my work, we're referring to the 8 serious offenses that make up the FBI's traditional index crimes. These are the crimes most consistently tracked for comparisons over time across jurisdictions. Part 2 crimes include everything else, from simple assaults and drug offenses to disorderly conduct and even DUI. They're still important, but they're considered less serious and not part of the official index that agencies use to track major crime trends. The index crimes, the 8 felonies I mentioned, fortunately are typically rarer? More rare. Whatever. They don't occur with as great a frequency as the Part 2 crimes. That's good for people, generally good for communities. So I'd like to get rid of this now and close out the attribute table here, and we will create our first joined buffer layer. Remember, our goal here is to join crimes to the buffer layers so we can get a sense of how many crimes occur within those layers, and then we can calculate the crime densities. So to accomplish that, we come up under Tools, type in Join Features, click Open the tool. Our first target layer will be the buffer zones with non-overlapping rings. The join layer is the crime data. We'll do a one-to-one join. We'd like to keep all target features. In the event that some buffer zones do not have any crimes, we still want to keep them in our new layer that we're going to create because we want to keep the buffers consistent across the 2 different types. So when you see this option to keep all features, check that box. The spatial relationship we'll specify is the intersects. That means that any crime that falls within the boundaries of any buffers will be included. We're not working with time, so there's no temporal relationship, and we can just get started. Click Run, and once it finishes, you'll see that the new buffer layer with the joined features is in the table of contents. So let's open up the attribute table, get a sense of what we're working with here. As with the original buffer layer from which it was created, this one has 3 features, and the new field that it brought in was the count variable. This is the count of crimes that exist within each buffer zone. And we can easily sum this by right-clicking Count, click on Explore Statistics, and over here we can see the sum variable. 6,648 crimes fall within the buffer zones with the non-overlapping rings. Let's get out of here. And I want to zoom in to show you what this looks like down close. This is the buffer layers of the non-overlapping rings. And you understand now that all these crimes that occur on top of these rings are included in that join features analysis. I'd like to go into symbology. I'm going to uncheck the 1200 and 800 foot buffers so that you can see just the 400. So you'll see the crimes that were counted within the 400 foot buffer region. And then if I click on the 800 foot area, you'll see the crimes now that are included there. And if I deselect the 400 foot area, you can see essentially the donut effect. So here, for example, these two crimes are not included in the 800 foot ring. All the rest out here are. If you look at this school, there are multiple crimes in the 400 foot zone that are not counted in the 800 foot zone. If I select just the 1200 foot zone, you'll see the organization of crime there as well. So nothing within 800 feet is included here. This is the mutually exclusive, non-overlapping buffers. This is a great buffering technique that allows us to examine crime densities in successive rings in mutually exclusive ways. We're going to click out and we'll create the next buffer, which is the multi-ring buffer with overlapping disks. To do that, we go right back into Tools, Join Features. This time our target layer is the multi-ring buffers with overlapping disks. Go back to Crime. It's a one-to-one join. Again, we keep all target features. Our spatial relationship is intersect. And again, because we're not working with time, we're ready to go. So click on Run. Once the tool finishes, it'll place the new buffer layer back into the contents pane. I'm going to uncheck the non-overlapping rings. First thing we should do is open up the attribute table, and we can see that we've got 62 features, just like the first buffer layer on which this one is created. Every high school gets 3 features, a 400, an 800, and a 1200 foot buffer. And every high school also gets a separate count of crime in those 3 buffer zones. And you can see that here. If we want to know how many crimes occurred total within the buffered region, we go to Count, Explore Statistics, and come over here to Sum. That number is 10,582, much larger than the crimes assigned to the buffers with non-overlapping rings, but that's because these buffers are cumulative, as I'm going to go through now. So let's close out this table, go into Symbology, and once we get it visualized by distance, we can see what's going on. I'm going to deselect the 1200 and 800 foot buffers and show us just the 400 foot ring. And just like the buffer layer with non-overlapping rings, the 400 foot zones of the overlapping disks look the same. You have all the crimes that occurred within 400 feet of the school, and they're here. But if I activate the 800 foot buffer zone, you'll see that the crimes that occurred within 400 feet are also included in this 800 foot disk. And when I activate the 1200 foot ring, we see that the crimes that occurred in all the buffers are included here. The overlapping disk configuration of this buffer layer is great if an analyst wants to understand how many crimes occur within 400 feet of a school, and then how many crimes occur within 800 feet of a school, and how many crimes occur within 1200 feet. So these buffer configurations allow us to answer 2 different questions essentially, but they also allow us to examine crime densities and compare those densities across one another, which is what we'll do now with our Excel table. So I'm going to clear out these selections, activate the non-overlapping rings, and pull up their attribute table. This is the simpler of the 2 buffer layers for us because there are only 3 features. So let's go ahead and copy these values, Control C, go back to our trusty Excel layer, and we are going to copy the crime values here. 681, 2591, 3366 for a total of 6,648 crimes, which we already knew. Now that we're here, we can calculate crime densities. To do that, simple division. We're going to say that this cell equals crimes at the 400-foot level divided by the square kilometers at the 400-foot level, and it's 663 crimes per square kilometer. And if we generalize that down, that's it for our crime densities here. So what does this tell us? The crime density is the lowest in the 400-foot area. It's quite high in the 800-foot zone and drops back down to a lower level, but still higher than the 400-foot zone once we get to 1,200 feet out. So let's go back to ArcGIS Pro and look at the other layer. I'm going to deactivate this layer and open up the attribute table for the overlapping disk layer. I'm going to bring this up a bit so that we can see more of the table. To copy and paste over the crimes from this one is a little bit more involved. The easiest way to do it is to put a definition query on this layer where we use distance, and we'll start with 400 feet. Click OK. And now we're only looking at the 400-foot buffers. And we can now, under count, we can go to explore statistics and get the sum here. 680. So we will copy that 680 into our Excel sheet over here. We lost one crime. Again, that's due to the way that the tool calculates the edges between the cumulative and the non-cumulative disks. So let's head back over to ArcGIS Pro, go back to Properties, and revise our definition query and look at just the 800-foot buffer here and rerun the Explore Statistics tool on just that column, and we get a sum of 3,260 crimes. Head back to Excel, enter it in, and of course, you'll see that by now at the 800-foot level, the number of crimes in the overlapping disk layer is much higher than for the non-overlapping buffers, and that's because, remember, these are cumulative. Head back to ArcGIS one more time to edit our definition query, just to look at the 1,200-foot regions, and we'll get a count here using Explore Statistics, and the sum here is 6,642. Back to Excel. So a total of 10,582 crimes occurred with the overlapping disk buffer configuration compared to 6,648. It's not double, but it's a sizable difference. And again, that's accounted for by the fact that the overlapping disks are cumulative. So now we can do some quick and simple math here. Equals crimes divided by square kilometers. And here we have it. So when we examine the crime densities here in the overlapping disk layer, we see a virtually identical pattern as we did for the non-overlapping buffer layers. The crime density at the 400-foot level for the overlapping disks is 661.89 crimes per square kilometer. It's very close to the density at the 400-foot level in the non-overlapping buffers. In the 800-foot area of the overlapping disks, we see 793.29 crimes per square kilometer, which is lower than what we saw in the 800-foot areas, but still much lower than our 661. At the 1,200-foot area, it drops back down to 718.34 crimes per square kilometer. So the numbers are somewhat different between the two buffer zones, but the patterns are identical. In both cases, both buffers show that around schools within that 400-foot range, crime density is the lowest. It jumps at the 800-foot level and then goes back down precipitously in the 1,200-foot zone across both buffers. So the numbers might be somewhat different, but the different configuration of buffers are telling the same story. I've got one more thing to show you, and that is this LQ column, which stands for location quotient. A location quotient measures how the concentration of crime in one area compares to a reference area. And in this case, it's how crime densities in the 800 and 1,200-foot zones compare to crime density in the 400-foot zone around schools. It helps tell us whether crime is more or less concentrated farther from the schools relative to the nearest zone. In our case, because we're using 400 feet as our reference zone, we'll calculate location quotients for just the 800 and 1200 foot areas. To do that, come back up here, we type equal the density of the 800 foot zone divided by the density of the 400 foot zone, and that returns 1.28. Next, we say this one equals the density of the 1200 foot zone divided by, again, the density of the 400 foot zone. Everything relates back to the 400 foot zone, and that's what we come up with here. We see that in the 800 foot zone, the crime density is 1.28 times higher than it is in the 400 foot zone. In the 1200 foot zone, crime is roughly 0.02 times higher than it is in the 400 foot zone. This gives us a quick and intuitive way to understand crime densities across the zones in relation to that inner zone. To calculate the location quotient over on the overlapping disk side, it's the same thing. This is going to equal the crime density of the 800 foot zone divided by the density of the 400 foot zone. And this is going to equal the density of the 1200 foot zone divided by the density of the 400 foot zone. And now we get a clearer picture here. It's a little bit more intuitive to interpret. On the overlapping disks side, the crime density of the 800 foot zone is 1.2 times greater than it is in the 400 foot zone. And in the 1200 foot zone, it's only 1.0 roughly 9 times greater than it is in the 400 foot zone. So again, in both cases, we see that close to school, within 400 feet of the school, there's a protective effect and the crime is the lowest. By the time we get out to the 800 foot area, roughly 2 blocks away, crime is the highest. And then as we move away another block or so at the 1200 foot zone, crime decreases again so that it's only minimally higher than it is at the 400 foot zone. And that's how you calculate crime densities across two different buffer types. And while the crime density patterns hold in both sets of buffers, the non-overlapping rings, in my opinion, give us a more reliable view of these variations. Because each ring is mutually exclusive, we're measuring change across distinct concentric zones rather than recounting the same crimes in overlapping geographies. That helps us see any real distance decay or displacement effects. The overlapping disks, on the other hand, are valuable for a different reason. They let us visualize how crime densities vary across individual schools, a great tool for mapping school-specific patterns, while the non-overlapping rings summarize those same relationships citywide in a single, clean comparison. These two different types of buffers allow for two different types of visualizations. In this series of tutorials, we focused more on the construction and interpretation of the tools themselves and less on the final visualization possibilities. In a future video, we might dive deeper into how different forms of geographic buffers, including those built around polygons, can expand what we see and how we interpret spatial crime data. For crime analysis, both buffer types have value. The disks highlight variation between schools, while the rings highlight variations between zones. And together, they give us a richer picture of how space, distance, and guardianship affect the geography of crime around schools. Thanks very much for watching. Hope to see you again.